Thank you very much for the invitation to present here. Very happy to be here. And I was initially thinking about talking mainly about links between biodiversity and climate. But given the context of this session, I would also try and orient what I'm going to say towards environmental health, towards human health, and talk more generally about the importance of biodiversity on our planet. Let me first begin by giving a brief recap of biodiversity through time, through deep time. The increase of complexification in biology over time has not been a tranquil, quiet river going through time, but life has been interrupted several times by massive extinction events. Okay, we know of, in particular, of 5 mass extinction events. There have been several other smaller ones as well. But these mass extinction events were responsible for removing at least 90% of the biodiversity on our planet from estimates of the fossil record. Now, if we look in particular what caused these events in the past, what we see is, by and large, these causes of mass extinctions are due to violent changes in the planetary carbon cycle. It's where the carbon is on our planet that really determines, what's going on. So carbon can be in the ground in the form of calcium carbonate, limestone. It can be in the form of coal, oil, gas, buried in the ground. It can be in the atmosphere in the form of carbon dioxide. And what determines the transition between the two is where you can often see causes of these mass extinction events. Those can be volcanic activity, releasing a lot of CO2 into the atmosphere. On the other hand, we can see the influence of biology, very importantly, in particular through photosynthesis, in taking carbon dioxide out of the atmosphere and converting it into life, which ultimately gets sequestered into the ground. So it's the transitions through where the carbon is, either in the ground or in the atmosphere, that is oftentimes very important in determining, the state of biodiversity on our planet and the causes of these mass extinction events. So we should clearly then be pretty worried about what's going on today, the increase in carbon dioxide in the atmosphere due to the burning of fossil fuels. Here you see the state of carbon dioxide in the atmosphere over the last 800,000 years from data from ice cores from the Antarctic, and we see very clearly that we're in a region of atmospheric carbon dioxide that we haven't been in for at least the last 800,000 years or so. So we should start to worry then about what is happening to the life on our planet, the biodiversity on our planet, and we've been doing that now for quite some time. This is the report of the IPBES, the equivalent of the IPCC for biodiversity, their last report from 2019, and here we see the global extinction risk for different groups of animals in particular is shown on this plot. And this is relating also to the famous red list of the IUCN. We can see how those red list species are increasing over the last 40, 50 years or so. So all of this is concerning, but how does this relate to those 5 mass extinction events of the past? This is one, perhaps most famous study that has been done in this regard, that was published several years ago, which compares the rates of extinction today with what we think happened in the past. And the most telling quote from this paper is the following, that if all threatened species become extinct within 100 years, and if that rate continues unabated, then terrestrial animal extinction would reach these big 5 magnitudes in perhaps as early as 240 years. Okay, so it's not tomorrow, but it's not millions of years away either. Okay, so indeed, we should be pretty careful and concerned about what is happening to the life on our planet. Of course, biodiversity is not something that is aesthetically pleasing, something that we can appreciate when we go for a walk in the forest on a Sunday afternoon, but it's also something that has extrinsic value. This value we can translate in terms of value at the level of genes, which provide resilience in agriculture, for example, in our crops. Resilience at the level of populations, for example, our fish stocks, so important for our fishing industry. Species are incredibly important for many different aspects of how life works on our planet. And individual ecosystems responsible for the diversity of our landscapes, which again promote resilience to environmental impacts, to environmental change, and so on. So there's intrinsic value in biodiversity way beyond the simple, aesthetic value of life. This has also been translated through into economic value. This is one study that was done, it's quite old now, from 2010 at the World Economic Forum. I'm sure there are studies more advanced than this now. Really trying to equate what the loss of biodiversity means in monetary value for different sectors of today's society. One of which, infectious diseases. And we've had a clear example of the link between loss of environmental or the intrusion of human activities on the environment that likely led to the COVID epidemic a few years ago, for example. So we can see the value of biodiversity also in terms of economic value as well, which is one aspect as we try to think about what a resilient society would look like in the future. So how is climate change affecting the ocean, which is what I'll talk about for the rest of my presentation? We have very clear data showing the consequences of human activity in the ocean in terms of sea surface temperature. We have actual data from 1900 showing how sea surface temperature has increased. We have global average sea level change increasing slowly but surely since 1900. Sea ice in the Arctic has lost about half of its surface in the summer months. And we have very clear evidence that seawater is truly acidifying as a consequence of carbon dioxide mixing with water, making carbonate, which is acidic. So we have data since the 1990s about this from the Pacific, from the Atlantic Ocean, time series data showing very clearly the increase in acidification in our world's ocean. So all of this is real data. It's not simulated, it's not models, it is real data from the ground showing how our oceans are changing in front of our eyes. And this is a particularly disturbing plot that I thought I should put up, showing the daily sea surface temperature in our global ocean from 60 degrees south to 60 degrees north. So Arctic, Antarctic is not in here, but this is our global ocean. And here we see the changing trends over an annual cycle in the global ocean. And we see how from the 1970s, the temperature of the ocean, of our global ocean has steadily increased. And then we saw this in 2023. We sort of see a step change. Something has happened in the ocean in 2023. This is up to November, 1st of November 23. This trend continues. And perhaps we've hit some sort of tipping point in the ocean. We don't really understand what's going on in the ocean, but clearly there are massive changes going on in the ocean as a consequence of climate change. How does this relate to human health? Well, there are several indirect and direct effects of how the ocean affects our own health. Indirect effects, we can think about the generation of oxygen in the ocean, which is pretty important for us to breathe, obviously. The ocean absorbs about 90% of the heat in the atmosphere. It absorbs about a quarter of the carbon dioxide emitted from fossil fuels. So the ocean is very important in regulation of our global climate, okay? Extremely important. So this obviously affects us all indirectly. And then there are the direct effects. For example, 1/2 of the world's population lives within 100 kilometers of the coast. So as the sea levels are rising, that's going to affect an awful lot of people on our planet. Consumption of contaminated seafood, swimming in polluted water, exposure to toxins from harmful algal blooms, are all negative sides of change in the ocean. The oceans are, however, also a source of new drugs for medicine. There are many examples of that, coming from sponges, coming from ocean microbes, coming from corals, and so on. And then direct effects also relate to disease transmission, as Andy mentioned already, the Vibrio example, which was first disentangled in the 1990s through pioneering work of Rita Colwell in Bangladesh, showing the relation between Vibrio in the ocean and zooplankton and incidence of cholera on the ground. So this leads me to the fact that the ocean is a microbial world. It's primarily a microbial world. There are pathogens in there, but there's also a lot of good microbes, a lot of microbes that are really there to ensure the health of our oceans, to ensure the well-being of our oceans. Much like the human gut microbiome assures our state of health, our state of well-being to a large extent, the microbes in the ocean perform the same functions in assuring the health of the ocean. Performing all sorts of important functions, also because these guys are where the biodiversity pool in the ocean lies. The microscopic life in the ocean represents 2/3 of the biomass in the ocean. The other third are the fish and the dolphins, the things you see on TV. But it's this 1/3 of microbial life which is incredibly important for running the show in the ocean, basically, providing all kinds of incredibly important activities. And even though the biomass of these microscopic organisms in the ocean is dominant in the ocean, they are nonetheless minuscule with respect to the biomass in terrestrial environment, which is largely plants. The land is green, so it's plants that dominate in terms of biomass. In the ocean, the microbes dominate in terms of biomass. And even though, they only represent a small amount of biomass, they perform the same levels of photosynthesis as do the plants on land, very similar 50-50 ocean-land, in terms of carbon fixation photosynthesis, and also in terms of fixed nitrogen. So nitrogen in the soils from rhizobia are extremely important for agriculture, and also in marine environments, nitrogen fixation is equally important. So there's all kinds of important activities that are carried out by this invisible world in the ocean, and we have learned more about this invisible life in the ocean perhaps through the Tara Oceans expedition, which was carried out about 15 years ago now, a 4-year expedition, which went out into the global ocean to explore these marine planktonic ecosystems and learn more about what they're actually doing. This work now has, from the Tara Oceans Consortium, has led to multiple publications, multiple information about all of these different kinds of organisms that are present in this microscopic world of the ocean. And we were very happy to see our work, our efforts acknowledged in an editorial in Nature a couple of months ago on the 8th of June 2023, where they talk about the work of the Tara vessel and in particular the Tara Oceans expedition in revealing this world of microbial diversity in the ocean. So through this project, we've essentially generated a baseline of life in the ocean at the beginning of the 21st century. So it's important to ask if perhaps we can use this to address how the oceans have changed in the past and how they're going to change in the future, to help us understand what the consequences of climate change will be on the ocean, and ultimately what those consequences may mean in terms of environmental health, human health, our societies, and so on. So I'm going to give you two examples of that. Hopefully I have enough time. I'm going to give you two examples. One example digging into the past to see how the oceans have changed in the past, and another example looking into the future. In both cases where we have leveraged this baseline data from Tara Oceans of life in the global ocean in today's world. So the first example I'm going to give you is about evidence the effects of ocean acidification on life in the ocean. This is a bit challenging if you think what you would like to do here. We would like to take today's ocean and compare it with the ocean as it was before the Industrial Revolution, right, to see how things have changed. The problem is we don't know, we don't have samples from the ocean from that time, or we have at least very few samples that we can compare today's ocean with. But we are lucky in one regard that we have samples collected by the very first oceanographic expedition in the 1870s, which was run on the HMS Challenger vessel, I think perhaps even funded partly by the Royal Society, not sure. Where these guys, they went out for 5 years, global ocean, looking at life in the ocean, brought back loads of samples, did lots of amazing things with it, and then those samples have now conveniently been archived in the Natural History Museum in London. And so what is possible to do is to take the samples that we collected in today's ocean, on Tara Oceans, for example, to compare them with those samples collected 150 years ago on the HMS Challenger. And this study in particular was interested to look at the effects of acidification by looking at the level of calcification of the shells of foraminifera, single-celled organisms, which produce calcified cell walls around their cells. And we know that calcification is a process very sensitive to acidification. So we would perhaps predict that the calcification has been affected by increasing acidification in the ocean over the last 150 years. So this is one image of a foraminifera taken, sampled by HMS Challenger 150 years ago. And in blue, we see here the thickness of the calcium carbonate cell wall around the cell. And we're comparing this with an equivalent foram collected by Tara 150 years later. And you can see that the thickness of the cell wall is clearly very different between the two. This paper is supported by thousands of other analyses indicating, you know, this potentially direct impact of acidification on calcification in forams. And this is one of the very, very few examples where we can really see how the changing pH of the ocean is having a real consequence on ocean life. So that's the sort of thing we can do by digging into the past. The second example is looking to the future, so projecting changes in a future ocean. So as I said, Tara Oceans generated a baseline of life in the ocean at the beginning of the 21st century. We can use that information to generate diversity plots, biodiversity plots of different kinds of organisms, be it photosynthetic bacteria, for example, or copepods, which are a kind of zooplankton. And we can plot out global biodiversity of each of these different kinds of organisms at this planetary scale. We see diversity is highest around the equatorial regions, tapers off towards both poles, as is the typical case also. The famous latitudinal gradient of biodiversity, first observed by Humboldt on land, and here shown for the first time for the global ocean. So with this data of the state of biodiversity in the ocean today, we can throw these organisms into the virtual ocean that is projected to be present by N2100 from the IPCC climate models. Okay, so these models consistently show increases in temperatures by end century throughout the global ocean. They show changes in primary productivity, in photosynthesis, and show other changes as well. So we can take today's plankton, throw it into this future ocean, and see, how biodiversity is perhaps projected to change over time. And this is a summary where we can see projected diversity anomalies in these 6 different groups of planktonic organisms by end 21st century. And you can see there's quite a lot of color in indicating changes in anomaly for each of these different groups, which is concerning, okay, but is perhaps most informative when we take those anomalies and plot them out latitudinally and compare them with global maps of, for example, carbon export, representing the capacity of the oceans to sequester carbon dioxide from the atmosphere into the deep ocean. Those anomalies with respect to fish landings, the fisheries industry. Fish eat the plankton, so when the plankton change, fish populations are going to change as well. And then these anomalies also shown with respect to the density of marine protected areas in the ocean. So these are areas where we try to preserve the biodiversity in the ocean, and we see in this map that these are areas that are going to perhaps be affected quite strongly by changing diversity in the future. So these are ways in which we try to see how biodiversity in the ocean is being affected by climate and how it may be affected in the future. And in closing, just let me say that the oceans also have great potential for carbon dioxide removal, for geoengineering programs. In terms of carbon dioxide storage capacity, the oceans are right way out here, extremely interesting for geoengineering. But on the other hand, there's a huge number of unknowns in this, in using the ocean for geoengineering because of our lack of knowledge about how the oceans actually work. So there's potential for the ocean to be used to help us even more to combat climate change, but many unknowns associated with that. And I will end there with a summary of what I tried to talk to you about today. Thank you.